Hello friends and welcome to this video. We are with the sixth chapter adaptive filters to learn the subject advanced digital signal processing. And so far after introduction to adaptive filtering system identification, we have been designing the finite impulse response adaptive filters. First of all, understanding the use of steepest descent algorithm and then the LMS algorithm here, for which the convergence we have addressed, the normalized version we have seen along with few of the other versions here. After the use of gradient adaptive lattice filter for the efficiency here, just now we have addressed the joint process estimator so that the applicability of the designed adaptive filter will be there acceptable to a variety of more applications here. So among all these applications, channel equalization is the most important and popular application here, where the use of adaptive filters benefits a lot here. So therefore, we have the current topic that is titled channel equalization in this particular chapter. So let us see what are the details, how the channel equalization is achieved with the help of designed adaptive filters. So let us begin with the topic. So here we can start with our topic, the topic titled channel equalization. So as we see the topic title here, we find the two terms. First one is the channel and second one is the equalization. Second term is a procedure. It is in the context of the first term. So if you have a background of the communication engineering, so there it is a simple structure. On the left hand side you can assume a section as a transmitting section. On the right hand side you can assume a receiving section. So right from source in the transmitting section to the destination to the receiving section here, we have to transmit the information, and that is through the communication channel. There can be a variety into the communication channel, and practically there it is the occurrence of interference or the noise signal interrupting into the original information causing losses here. So the equalization of the channel most of the time we prefer here. So we will have just a brief look for this problem of the adaptive channel equalization here. And the adaptive equalizers are the devices which are really very necessary for reliable communication of the general digital data here. So where practically the channels, communication channels are not the ideal ones here. So the basic operation of the digital communication system with the use of notations we have been carrying forward throughout this particular chapter, let us discuss here. So we have the usual notation D of n to be a digital sequence that is to be transmitted across the non-ideal channel I can see here, where the D of n will have the values of plus or minus 1 here. Now this is what the sequence, the input sequence provided as input to the pulse generator. If we see the structure to be in the form of a block schematic here, and this pulse generator will produce a pulse of the amplitude level denoted by capital A at the time small n if d of n is equal to plus 1, and the pulse of the amplitude in the reverse side we have minus capital A if d of n is equal to minus 1. So this is what the sequence of pulses that is further modulated, and then it is transmitted across the communication channel to the destination place here, what we can call receiver section here. So this is supposed to be at a remote place here. Now at the receiver side, when we receive that particular signal, the signal reaches that particular place through the receiving antenna here, there it is the process of demodulation here, and the samples the received particular waveform and that produces a discrete time sequence, generally we denote as x of n. And ideally, if x of n is equal to the desired signal d of n, in the practical case this is not true here. Most of the time we have the losses of the information, that is why x of n is never equal to that of d of n here. So behind having the inequality between the d of n and x of n, there are two possible reasons. The very important reasons are there. So the first reason is that the channel is never ideal and it will have certain kind of distortion. For example, it is the inter-symbol interference. And the second reason is that whatever the signal in the form of a waveform we receive at the receiving or the destination end here, it will have invariably content of the noise here. So let us have the assumption that a linear dispersive channel, a model for the received sequence x of n, is described with the help of the expression where we have x of n equal to the summation k is equal to minus infinity to small n for the multiplication of d of k with h of n minus k. The multiplication is added to v of n here. So the notations in this particular expression, here we have h of n to represent the unit samples response of the channel here, whereas v of n, the right hand extreme term, is the additive noise here. Now when we have the received sequence, as just now we have denoted by x of n, the receiver will make a decision as to whether a pulse positive one or the minus one is to be generated here, and this is of course at the time small n here. So this decision is typically made with the simple threshold device here that can be described. So it is actually the estimate, that is why we have small d cap of n to opt the value positive 1 for x of n greater than or equal to 0, whereas it will opt the value minus 1 for x of n will be equal to less than 0 here. So now in order to have reduction into the chances of making the error, we want the perfect signal to be decoded at the receiving end. The receiver will employ the equalizer. So this is our topic of interest, that is channel equalization here. This is in order to reduce the effects of channel distortion here. And since the precise characteristics of the channel are unknown practically, the possibly time varying constants are there. The equalizer is typically an adaptive filter. So this is the use of this particular design of the adaptive filter there for the channel equalization purpose here. So let us visualize a simplified block diagram of the digital communication system that just now we have discussed. So here it is, the transmitter section on the left hand side. There it is, communication channel through which the signal is transmitted to the receiving section, and in the receiving section here we have shown the equalizer block here. The notations we carry forward. So d of n, the desired signal to reach the destination here, where with the help of the equalizer we denoted d cap of n here. So x of n is the signal, that is d of n added by the noise signal v of n while having a journey through the communication channel here. And as the equalizer is built up with the help of the adaptive type of the filtering here, there it is, the use of error signal e of n, that is continuously updating the values for the equalizer to produce the best estimate of the desired signal denoted by d cap of n here. So as we look at this particular block schematic, there it is necessary to have generation of the error signal so that the adaptive filter will work efficiently for the channel equalization purpose here. There are two methodologies that can be used for generation of the error signal. The first one is the training method and the second one is the decision directed method. Regarding the training method, we have the information that the training method is occurring during the initial training phase that we have represented in the block schematic. The training phase that is pointing from the left hand side to the right hand side here. So this is occurring when the transmitter and receiver first establish a connection between them. So there it is, a signal to be received here, and during this particular phase the transmitter will send the sequence of pseudo random digits that is known to the receiver here. So it is just like a password here, and with the knowledge of d of n, the desired signal, the error sequence is easily determined and the tap weights of the equalizer may be initialized here. So after the training method, we have the alternative option to be the second methodology called as the decision direct method here. So once the training period has ended and the data is being exchanged between the transmitter and the receiver has no prior knowledge of what is being sent here. So there it is, one important and very interesting scheme that may be utilized for extraction of the error sequence from the output of the threshold device that we have in illustrated form. Let us visualize this illustration. So here we have it. So here we see x of n as input. The x of n we have obtained from the communication channel, which is non-ideal here, and this is fed as input to the channel equalizer, which is of the adaptive type here. So it is supposed to generate the signal y of n as the output signal here, and from this, with the knowledge of d of n, we are having the e of n generated here, and the second block is a decision making block here, with the help of which we have d cap of n, the best estimate here. So at a specific case here, if there is no error on the output of the threshold device, so we can say that d cap of n is exactly the same d of n. So that time the error sequence may be formed by taking the difference between the equalizer output denoted by y of n and the output of the threshold device. So here it can be denoted as e of n is equal to y of n minus d cap of small n. So because of this, the particular approach is called as a decision directed methodology. Now coming to the exact details of the channel equalization process in the adaptive way, let us have the representation in mathematical expression form here for the channel equalizer unit samples response, that is denoted by h of n. So h of n for n is equal to 1, 2, 3 and so on will of the value computed by half added to 1 by 2 times cosine of 2 pi in the bracket n minus 2 divided by w. Otherwise, it is opting the value 0 here. So additionally, to controlling the amount of distortion introduced by the channel, the parameter w that we see in the denominator of the first condition will affect the eigenvalues of the autocorrelation matrix capital R suffix x of the received signal x of n. Now making the use of this expression for the unit sample response of the channel equalizer block here, our model for the input signal to be processed at the receiver end, that it is denoted by x of n, will be equal to d of n, the desired signal convolved with the unit sample's response, that is h of n from the above equation, and this convolution result is added by the noise signal v of n. Now here d of n is a sequence of uncorrelated random variables, and therefore v of n, the noise signal, white noise having certain variance that we can denote by sigma suffix v square, and v of n being uncorrelated with d of n, the autocorrelation sequence of x of n we express as r suffix x of k is equal to h of k convolved with h of minus k. This convolution result is further added by the variance sigma suffix v square multiplied to del of k here, that is the impulse here. And since h of n is non-zero only for the values of n is equal to 1, 2, 3 and so on, here we have Rx of 0 is equal to h square of 1 added by h square of 2 added by h square of 3 added by the variance sigma suffix v square. Rx of 1 is equal to h of 1 into h of 2 added by h of 2 multiplied to h of 3. Rx of 2 is equal to h of 1 into h of 3, and the Rx of k, the autocorrelation value, will be equal to 0 for all the values of k greater than 2 here. So finally, the autocorrelation matrix of x of n will be a Toeplitz matrix having the form represented capital R suffix x is equal to Toeplitz of, here we have the elements Rx of 0, Rx of 1, Rx of 2, and rest of the elements are equal to 0. So this is the quint diagonal matrix, that is only non-zero elements are along the main diagonal and the two diagonals above and below the main diagonal here. Now for the autocorrelation matrix, there are the eigenvalues which affect the convergence of the adaptive filter and that depend on the value of capital W as indicated in the previous equation, as well as onto the size small p of the autocorrelation matrix, which is equal to the number of coefficients into the adaptive filter, what we can call the order as well here. So there can be a brief tabulation for the maximum and minimum eigenvalues of the autocorrelation matrix. Now let us have, for example, the upper bound, the largest value of the autocorrelation matrix as the largest row sum for p greater than or equal to 5 denoted by lambda suffix max. Lambda is the representation of the eigenvalue. So for the largest we have lambda suffix max less than or equal to Rx of 0 added by twice Rx of 1 added by twice Rx of 2. So for example, for the given values of W simply, the consideration we can make with certain tabulations that you can find into the textbook. Lambda max will be less than or equal to 1.8998 when we consider W is equal to 2.8. The complete tabulation you can find. I have selected values here. Lambda max can be less than or equal to 2.2550 when W is equal to 3.0, and lambda max can be less than or equal to 2.6207 for W is equal to 3.2. So for the example of channel equalizer under consideration, let us have assumption that beta is equal to 0.3, W is equal to 3.0, and the order P is equal to 15. So that time the equalizer, channel equalizer, is first of all initialized using the training sequence, for example of the length 500 here, and here we visualize the convolution of the unit sample response of the channel that we have denoted by h of n with the unit sample response of the equalizer w of n at the end of the training sequence here. So here we see on the horizontal axis the markings 0, 2, 4, 6, 8, 10, 12, 14, 16 here, and on the vertical axis we have the markings from minus 0.5, 0, 0.5, 1 here. And since this is what the convolution approximately unit sample at n is equal to 8 that you can see here, rest of the places we have 0, the equalizer is good approximation to the inverse of h of n. Now after the training sequence, the equalizer will not be having any kind of knowledge of the desired signal to be received correctly at the destination, that it is d of n here, and it has to rely on the decision directed adaptation to have generation of the error sequence to drive the coefficient update equation that we have mathematically shown here. Now let us visualize a received sequence that we have x of n denoted in the mathematical relations, and this is for example the first 100 values after the training period here. And next to that we see the output of the adaptive equalizer here. This is what the adaptive equalizer output here. So in this example, as we see, due to the presence of the noise, the equalizer is having the estimation of the signal here, and with the help of the threshold device, the estimation can be utilized to correctly decode what it was transmitted from the source side here. So d cap of n, that is the estimate of the desired signal, will match d of n, the desired signal, after the estimate has been utilized by the threshold device here. So this was our topic to discuss the popular application of channel equalization by using the adaptive type of the filtering here. By the next lecture, we shall continue into the same chapter, chapter number 6, that is adaptive filters here, and we shall address the topic adaptive recursive filters. Thank you.